All right, let's talk about Apache Spark's structured streaming. We're going to see how Spark helps you completely shift your thinking away from those old school clunky batch jobs and start building some really powerful real-time applications using a model that is, believe it or not, surprisingly simple. Okay, so to really get this, let's look at the old world versus the new world. On one side, you've got traditional batch processing. Think of it like developing a roll of film. You got to gather all the data, run one massive job, and then maybe hours later you finally get your results. But on the other side, you have stream processing. That's like a live video feed. The data's endless, it's processed bit by bit, and the results, they're practically instantaneous. But that live feed of data brings with it a huge challenge. A stream is, by its very nature, infinite. It never stops. And because of things like network lag, data can show up late or completely out of order. The whole system has to run 24/7. It is an absolutely unforgiving environment to build in. And that leads to the big, scary question that trips up anyone used to working with nice, predictable, finite datasets. How on earth do you run a reliable query on a table that just keeps growing forever? Well, this is where Spark's solution comes in, and honestly, it's kind of genius in its simplicity. Spark basically says, hey, stop worrying about the infinite stream. What if you just thought of it as an endless series of tiny, manageable tables? And this is the core idea right here, the unbounded table. Spark wants you to just picture your live data stream not as this chaotic torrent of information, but as a simple, logical table where new rows are just constantly being added to the end. I mean, that one mental shift is the entire key, because it means you can use the exact same batch-style queries, the same SQL and data frame APIs you already know and love, to analyze a live stream. So how does it actually do this? Well, under the hood, structured streaming is just running this constant, simple loop. It checks the source for any new data, bundles it up into a tiny micro batch, processes that little batch with the super powerful Spark SQL engine, and then updates your final results. And then it just does it again and again and again, forever. And please, don't let that word batch fool you. We are not talking about minutes or hours here. This microbatch engine is so incredibly fast that it can get end-to-end latencies down as low as 100 milliseconds. For almost every application out there, that is real time. Okay, that all sounds great in a perfect world, but, reality is messy. Data doesn't always show up on time. A user clicks something on their phone, but that event might not hit your servers for several minutes. How do you deal with that? Let's look at a classic example here. An event happens, let's say someone types a word, at exactly 4 minutes past noon. That's what we call its event time. But due to, bad cell service or network lag, it doesn't actually arrive at our application until 11 minutes past noon. So if we're doing analytics and counting words in 10-minute windows, that late word clearly belongs in the 12 to 12:10 bucket. But it showed up at 12:11. If we only look at the arrival time, our counts are just going to be wrong. So how does Spark solve this puzzle? The solution is this really clever feature called a watermark. I want you to think of it like a moving deadline for late data. It's a way for you to tell Spark, look, I'm willing to wait this long for late events to show up, but after that, we're moving on. This is so important because it stops the system from having to keep old time windows in memory forever. And here's how it works in practice. It's super elegant. You just tell Spark two things. First, which column has the actual event's timestamp, and second, how much of a delay you're willing to put up with. Let's say 10 minutes. As your data flows in, Spark just keeps an eye on the latest timestamp it's seen. The watermark is then always calculated as that max time minus your 10 minutes delay. Any data that shows up with a timestamp older than that moving watermark, it just gets ignored. And, this is the crucial part, that's the signal to Spark that it can safely clean up the memory for that old time window. All right, so we've got a handle on late data. The next tool in our toolkit tackles an even bigger, scarier problem: failure. In a 24/7 streaming world, things will go wrong. So how do we make sure our system is rock solid and resilient? Look, a streaming job is meant to run forever. It's not a question of if something will crash, but when. A server dies, an application gets a bad update, whatever. You simply cannot afford to lose data, and you definitely can't afford to process it twice. Spark's answer to this is a mechanism called checkpointing. The best way to think about it is like a super smart industrial strength bookmark for your stream. Periodically, Spark just saves its exact progress, everything it needs to know, to some reliable storage like S3 or HDFS. And we're not talking about a simple bookmark here. The checkpoint saves everything: the query's configuration, the exact offset it's read up to in the source, the current batch ID,
And most importantly, any stateful info, like those running word counts we were calculating earlier. So if the query fails, it can restart and pick up at the exact spot it left off. Now, here's where it all comes together beautifully. When you combine this powerful checkpointing with two other key pieces, a source that lets you replay data, like Kafka, and a destination that can handle duplicate writes gracefully, you get this holy grail of streaming called end-to-end exactly once semantics. It sounds fancy, but it's a simple, powerful promise. No matter what failures happen, every single record from your source will be processed and saved exactly one time. No data loss, no double counting. Ever. Okay, last piece of the puzzle. We can handle late data, we can survive failures, but how do we control the rhythm of our stream? The speed, the timing, and even the cost? Well, that's done using triggers. The processing time trigger is your workhorse. You just tell it to run a micro batch every 10 seconds or every minute. The Available Now trigger is amazing for saving money. It spins up, processes all the data that's piled up, and then shuts down. Perfect for a job you only need to run once an hour. And then for those extreme, ultra-low latency situations, you have the continuous trigger, which basically processes data the very instant it arrives. So let's pull all of this together. What's the big picture here? What's the main thing you should walk away with? It really boils down to these three core tools. Watermarks give you sane control over time and late data. Checkpointing gives you that bulletproof fault tolerance and exactly once guarantee. And triggers give you fine-grained control over latency and cost. You put those three together, and you have an incredibly robust and flexible streaming engine. But the real beauty, the absolute game changer, is that all of this heavy lifting is done for you. Structured streaming lets you build these incredibly sophisticated, real-time, fault-tolerant systems using the same simple, batch-like data frame and SQL queries you've been writing for years. It's a truly revolutionary way to think about stream processing. Which leaves us with one final interesting question to think about. This whole micro-batch model is a brilliant trade-off, giving you resilience, high throughput, and great latency. It's perfect for 99% of use cases. But what about that 1%? For those edge cases that require sub-millisecond latency, think high-frequency trading, is it enough? Well, that's when you might start looking at Spark's even faster continuous processing mode. But for just about everything else, this micro-batch model is your key to unlocking real-time data.